Hello, everyone. Good afternoon, and welcome to the inaugural webinar of the SimEA Project Seminar Series. Today, we will speak about the Computational Science and Engineering of Complex Materials, the SimEA ERA-Chair initiative. I would like first to introduce our speaker, Professor Vangelis Harmandaris. Professor Vangelis Harmandaris is the ERA-Chair holder of the Modeling and Simulations for Engineering Applications, the SimEA project, of the Computational-based Science and Technology Research Center of the Cyprus Institute. His main expertise covers the areas of mathematical modeling, computational modeling and engineering, soft condensed matter, thermodynamics, and complex polymer-based materials. He received his PhD in chemical engineering from the University of Patras in 2002 with a dissertation on the atomistic molecular dynamics simulations of polymer melt viscoelasticity. Following a postdoctoral position at the Institute of Chemical Engineering and High Temperature Chemical Processes at the Department of Chemical Engineering at the University of Patras in Greece, and at the theory group at Max Planck Institute for Polymer Research, MPIP, at Mainz in Germany during 2005 and 2009, Vangelis Harmandaris obtained a track tenure assistant professorship position at the Department for Applied Mathematics at the University of Crete in Greece. On September of 2016, he became full associate professor at the Department of Mathematics and Applied Mathematics, leading a computational engineering group until July 2020, where he's currently the ERA-Chair professor of the SimEA project of Castor C, the Cyprus Institute. Vangelis Harmandaris has published about 75 papers in refereed journals, 4 in books, 20 in refereed conference proceedings, and about 55 in non-refereed conference proceedings. He has given more than 120, about 70 invited presentations in international conferences and academic and industrial institutions. As of August 30th, 2020, he has received 33,179 total citations, and his age index is 30. He has been a reviewer for a large number of international journals, including for the European Union and for various institutions, among which the National Science Research Foundation in the US, the European Science Foundation, the Israeli Science Foundation, the National Research Council of Romania, and the Greek General Secretariat for Research and Technology. He has also been the organizer and co-organizer of 10 international workshops and conferences. Professor Harmandaris, please, the floor is yours.
Okay, thank you very much, Andreas, for this kind introduction. So welcome everyone in this first seminar of the SimEA Seminar Series. So as Andreas said before, my goal here today is to introduce you in the next, let's say, 40 or 45 minutes, to introduce you the SimEA, the new initiative at Castor C and the Cyprus Institute, and also to give you a few details about the research projects that we envision, let's say, to develop during this project. So the project, as you see here in the title, it is related with the Computational Science and Engineering. And this is the overview of the talk. So initially, I will give you a short introduction concerning the Computational Science and Engineering, the scope of the SimEA project, and a short introduction of the research team as it has been formulated so far. Then I'm going to present you a few details about the research directions that we plan to pursue, let's say, during the SimEA project. And all these directions are related primarily with every aspect of high-performance computing and data analytics for materials. As you see here, this cover from ab initio calculations up to atomistic and mesoscopic or coarse-grained, as we say, simulations, till the continuum modeling and finite elements up to the continuum level. And at the same time, we are also going to use and develop new data-based, let's say, machine learning algorithms in order to combine, to predict, to use actually to develop hybrid physics-based data-driven models, all of them for the prediction of properties of complex materials. Then I will give you also a few examples just from different systems that we have studied during the last 10 years, I would say, or so, primarily focusing on multi-component nanostructured materials and polymer-based most of the time. Then the last part, let's say, of the talk I will try to give you a short overview of the non-so pure, let's say, scientific activities of the SimEA and primarily actions related with innovation, which is the main part of the project. And we will close with a few remarks about the new era, as we quite often say that we are living now in the exascale era nowadays. So first of all, just a few introductory slides for the people who might not be familiar with what is computational science and engineering. So nowadays, computational science and engineering covers a very broad topic of different things, and it's by default, I would say, multidisciplinary field. So this is just a pictorial, whereas you see it is in the overlap region between science and engineering, which you would expect from the title, but at the same time, it covers, definitely, it uses and covers mathematics, because all the algorithms are more or less based on mathematics, and of course, computing. And in the heart, at the heart, I would say, of computational science and engineering, it's always the model. So the model, which is mathematical or computational model, and which again, if we have here in this triangle, it's between, let's say, computation, theory, and experiment. And as you see here, we have application, which is related, let's say, to science, then architecture, which is related to the computing environment, and algorithm, which is typically the mathematical model. So all of them are coupled together, and more or less nowadays, computational science and engineering refers to any kind of discipline. And this is not, I think this is entirely true, but in order now to discuss about computational science and engineering, we don't need only that, but we need also the machine. So these are coupled together with large-scale computational infrastructure, and actually the photograph that we see here, if I'm not wrong, is from the currently fastest supercomputer, which is named, I think it's Fugaku, it's from Japan. And of course, these are changing, every few months, but this is currently the fastest supercomputer nowadays. So as I've said before, computational science and engineering refers to a very broad range of potential applications in different fields. So now in the next few slides, I will give you just some examples from systems that we primarily consider under SimEA. It will be among our priorities. So a typical example concerns polymer nanocomposites. So polymer nanocomposites are multi-component materials. There is a polymer matrix, and then dispersed in the polymer matrix are some particles. In most of the cases nowadays are nanoparticles, which means very small particles with at least one dimension on the order of nanometers. And these are very important because the dispersed phase affects and alters the properties of the hybrid material. And because of that now, let's say, better properties of the hybrid material, polymer nanocomposites can be used to a variety of several different systems. You see here an application from our daily life, which is the tire materials, or all tire materials are polymer nanocomposites actually. But at the same time, they can be used, as you see here, from several applications related to energy, to sensing, to transportation, defense, information industry. So it's really huge, the field. And on top of that, the last 10 or 20 years, there is also a very, very broad family of different applications related to biomedical field. So as we see here, from biointerfaces related to drug delivery up to food packets, which is extremely important nowadays. So these materials are directly related with all these applications. So whatever we see more or less in our daily life. Another example now are graphene-based nanostructured material. Graphene is a very hot, I would say, and very popular material of the last 10, 15 years. There was the Nobel in physics a few years ago for the discovery of graphene. It's a 2D material with some unique, exceptionally unique properties. And since that, it is a potential application for, again, an enormous range of possible materials, from organic electronics up to what you see here, tissue engineering, up to drug delivery again, to 3D bioprinting, and whatever you can see. And the reason that is it's envisioned as a potential material for all these applications is primarily because of its unique properties, as you can see here, for example, but at the same time, it's relatively easy to functionalize it, and from that to change, let's say, the materials of the pristine graphene and to create new materials. And all of them now, such type of materials are related also with polymer thin films, as we call it here. So thin films, again, it's a family of materials that we use every day, even if we are not really aware of that. For example, in food packaging, in adhesives, electronics. So we all have mobile phones. All of them are nowadays consist of really very, very thin films of different materials, and in many cases of organic thin films, which are the polymer or less than macromolecular, let's say, structure. At the same time, you see here membranes, brushes, so materials with much different properties, up to clever, as we call, responsive materials, which are materials that change their properties based on the environment. An example is that we might see here a material which has different properties under air and different under the humid environment, and this again is extremely important from the point of view of application. And if now we discuss about, let's say, the engineering of these materials, the list is really endless. Now, a main characteristic, I would say, of all these materials, which are directly related with the multidisciplinary that we discussed before, is that all of them are really on the overlap of different classical, I would say, discipline fields. For example, the soft matter, what we typically discuss as soft matter, which is again a very broad family of different materials, is on the overlap between physics, chemistry, and biology. And I would say that on the background, it's always mathematics, when we discuss at least about theoretical or computational study, and computational science, because all these are extremely complex problems, so we cannot solve them analytically. And nowadays, I would say that computations is a necessity. And exactly because of all this now, this interdisciplinary nature of this phenomena and this approach, there is really a very broad family here of scientists, from physicists up to engineers, to chemists, to the theoretical chemists, to applied mathematicians, material scientists. Again, here the list is really huge. And all these people are working on such systems. This is really a big challenge now, the study of this material. And of course, now one question is, why computational in this part? So of course, we have the traditional engineering. Why do we need the computational thing? And I should have said that despite the fact that computers exist, let's say, the last 50 or even more years, the computational engineering is a relatively new discipline, because it deals directly with the development and application of computational models and simulations, and this model should be at least up to one point realistic in order to refer to real materials. So the simple, let's say, toy models are not really enough when we discuss about computational engineering. So the main idea is that we couple these computational models, the simulations, and the algorithms with high-performance computing, in order now to solve problems that arise or that are related either with engineering analysis and design, this is the engineering part, or with the natural phenomena, which we would say that is the computational science part. So both of them concern, of course, and they involve the word computational, which means that this is the main characteristic. And because of that now, and the recognition the last, I would say, a few decades, this discipline is recognized not only as a new field here, but as the third pillar of discovery next to theory and experiments. There are this very nice plot here where you can see that the scientific understanding for thousands of years was mainly achieved via experimentation and theory. So the last 50 years, let's say, if we want to extend a little bit, we could say that computation is really part of this way to understand things and discover things. And as we said before, this is actually, again, the overlap between computer science, mathematics, or applied mathematics and statistics, and all branches, really all here, branches of science and engineering. And in all cases, I would say that the holy grail in computational science and engineering is to produce and to have accurate models for quantitative predictions, which could lead, from the point of view of engineering, at least in the in silico design of materials and process. So the idea is, of course, to not perform experiments, but to do everything in the computers. And this actually nowadays is, maybe you have seen this before, but nowadays there is also a fourth pillar, or the fourth paradigm, as it's quite often called, This is the part of the evolving science. Initially, it was empirical, or as we say, experimentation, the theoretical branch, which was developed at least based on the modern physics a few hundred years ago. Then we had the last, as I said before, few decades computational part. Now today, or I would say the last 10 years, the data part is recognized as a new really field. And there was a very famous book a few years ago from people from Microsoft, actually, who discussed all this as the fourth paradigm. And this, it might be a little bit exaggerating, but up to one point, I think it's true, because the paradigm of discovery in data science is different than what it was before. So the idea is that in this case, we understand and we discover things based on the analysis of data, and this data can be can advance actually science. Now, from our perspective, it is very important to emphasize that computational science and engineering is directly related with both the high-performance computing, or what we discussed before as the third pillar, and with data science. So both of them are related with computational science and engineering. And of course, in order again to have all of them, we need access to infrastructure. So without infrastructure, neither the high-performance computer nor the data science could be. I mean, we should not forget that data exists for hundreds of years, even thousands of years. In ancient Egypt, they used to have large data sets, but of course, it was not possible to analyze them a lot, actually, and this was not even possible even 20 or 30 years ago. The fact that now we discuss about data science, it's exactly because of the infrastructure. And here you see PRAISE, which is the most well-known consortium of computational infrastructure in Europe, and actually the computational infrastructure here, the Institute, is part of PRAISE. So we're both happy with that. Okay, now a few things about the ERA-Chair. What is the ERA-Chair initiative, and what is the SimEA, as we call it, ERA-Chair? So this information might be boring for some of you, but on the other hand, for some of you might be interesting, especially in order to, if you want to see and to consider probably applying for something like that. So these are some initiatives that started in the previous Horizon program. Actually, it was even before the Horizon, but in the Horizon 2020, it was a larger action. And the idea is to bridge, let's say, to bring some excellence to academic institutions that belong to some specific countries, the widening countries. And the idea beside now the research part, that's why I want to insist, and I will emphasize this in this current talk, is that one of the main goals is that there should be some structural changes on the institutes in order to have to build something that's sustainable even after the end of the ERA-Chair. And this, as you see here, are the two main goals of all ERA-Chair initiatives. So an ERA-Chair should be in a specific research field. However, all of them should have these two main directions. First, to advance science by bringing high-quality people at the institute, and also to implement structural changes. And actually, as I said before, if someone are interested for that, I mean, this will be part of the New Horizon program as well. Now, this, just as the historical context, the SimEA is part of that action. This is just some of the statistics, and if I'm not wrong, Castor C has applied for that 2017, got the funding in 2018. The official start date of the project was 2019. However, of course, in order to attract people and all that, there is some period. So I've started 100% a few months ago, and the end date of the project is in almost 4 years from now. And this now is the main scope, I would say, of the SimEA, which, as you see here, is to advance computing and data science methods for Castor C and for the Cyprus Institute in order to solve primarily engineering problems, to create collaborative schemes with academia, public and private sector. I would say in general to create a computational engineering hub at Castor C. So we are open for new collaborations, new projects, new ideas. And actually, as you will see within the next months, we will try to reach you and contact you, several of you. I mean, in order to try to build new projects, and at the same time, as I said before, to build some structural changes that will be sustainable after the duration of the project. So next, I would like to introduce a little bit the team, because I really feel very lucky that we have already managed to attract excellent scientists and build almost the completed, I would say, the formation of the team. So beside myself, there is Nikos Sava, who is an assistant professor. He's an applied mathematician. I will not, it will be very short, the introduction, just to show you also this multidisciplinary nature of the research team, which I think, from my perspective, is essential, since all projects in computational science and engineering are by their nature multidisciplinary projects. So then we have 4 postdocs. Panagiotis Katsabapis, she is an applied mathematician. Petra Batsova, she is a chemist. Dimitris Mindis, a chemical engineer. And Wes Mahmoud, mechanical engineer. All of them have already started, or they will within the next couple of months. Then there are also 3 students, 3 PhD students, who are now starting their PhD. Nikolaos Patsalidis, a mechanical engineer. Eleftherios Christofi, applied mathematician. And Pavel Zerva, also applied mathematician. And beside that, there's another important thing. We have two very important supporting positions. The one is an innovation industry scout, Christos Christodoulou, a physicist with many years experience in industry, leading a team of, as you see here, a data scientist, a software engineer, and who will be, let's say, his main task would be to contact private or public sector as the innovation scout. And last but not least is our scientific coordinator, Kathy Christoforou, a chemist with expertise from her PhD in drug design, but also experience in coordinating research activities, and the coordination of the project will be her main duties under SimEA. So now all this team is really required to be interdisciplinary, and it was built on purpose, I would say, for this, in order to deal problems from different categories and from different fields. And here now you will see the main, let's say, research direction, as we call it, under SimEA. So the idea of the SimEA is to create, to start from some projects and then to create or to propose new projects that belong in this computational modeling of nanostructured material, as we call it here, or to develop new methods for large-scale simulations, hybrid methods, physics-based data-driven, as we call them, and all of them for large-scale applications, scalable codes for using large infrastructure. Then the third one is related with biomolecular systems. The fourth is related with something that is very now trendy in computational engineering and very important, actually. It's the uncertainty quantification of models. So the idea is that there are models, there are actually many, many models, even for the same system, so there should be a way to quantify the uncertainty of the models that could lead to model selection. And that typically these are performed via statistical methods. And the last part, I would say, which is related directly with all the previous, is the application of these codes on really high-performance computing as we go towards the exascale era. So this was a relatively long introduction about the topic, the field, and the team. So in the next now few slides, I will give you a few examples of the research that we have done the last few years on this field, and these will be the projects that we would like to pursue during the SimEA. So a big now family of systems concerns nanostructured materials and primarily polymer-based. A main now characteristic and a very important thing of such materials is that the presence of interfaces alters the properties, the macroscopic properties of these materials. And this is extremely important from the engineering point of view. So there's important questions related, for example, with how a substrate or a filler, let's say, affects the property of the matrix. And what is the physics of the interface? The physics in the interface determine also the properties at the macro scale. So here the idea is to design properties, to design algorithms actually, that could lead to the final end, to the materials with the desired properties. This is an extremely challenging and different problem, and typically I like to to add here the motto of Pauli, who's a very famous scientist of the previous century. So he quoted that God made the bulk, its surfaces were invaded by the devil in order to show exactly how complicated and how difficult is the study of these materials. And the grand, I would say, computational challenges there is to examine these interfaces at the atomic level, if possible, and to predict structural properties relations that could lead on the long end to the design and to the engineering design of these materials. Now, especially for polymers, this is really a main challenge, and the reason for that is that for polymers are associated with a very broad and extremely enormous, I would say, broad of length and time scales characteristic for such materials. So I assume a simple molecular chain, then this molecular chain is a simple molecule, right? So in that chain, there are time scales from the order of 10 to the minus 15 seconds, 1 femtosecond, which are related with the bond vibrations, all to the spectrum of times up to the level of second, which can be the relaxation time of the entire chain. So this is a big characteristic of macromolecular chains and polymers, because all these time scales exist within the same molecule. It's the only molecule that has all these time scales inside the same molecule. And of course, then when we have multi-component systems, these time scales get even broader. There are also associated length scales, starting, let's say, from the, if we are on the more detailed scale, from the atomistic or subatomistic up to the microscopic or atomistic level, to the mesoscopic, up to the macroscopic. So this now coupling of time and length scales requires also the usage of different computational methods in order to study such materials. And I'm sure that you have seen such plots before. These are typical qualitative plots where we have length and time scale, and in the plot you see different methods which more or less describe different window in this time versus length plots. And then you can see here that the more detail, as we expect, the description at the quantum level, then there is a description at the microscopic level, in the mesoscopic, up to the continuum. There are methods in different, in the different parts of this plot. However, a big challenge is to develop systematic, or as we say, rigorous models in order to bridge these different scales here. And this is the idea behind of what we call multiscale or hierarchical multiscale modeling, which involve actually combination of these different techniques. And you see here the overlap. The overlap here is important because we need to have a rigorous way in order to develop models from one scale, if possible, by using data from more detailed scale. So this is a bottom-up, I would say, approach. And in the next slides, I will give you a few examples from works in different scales. As we said before, the most detailed in our perspective is the subatomistic, is the density functional theory or the Venetian calculations. And here a main, for example, a typical problem is how a molecule interacts with the surface. This is a very important problem, a very important actual issue, because the strength of interaction can determine the properties. On the other hand, there is no experimental technique that gives us direct information on how a single molecule interacts with the surface. So especially for such type, for this property, indeed, ab initio or density functional theory is the only choice. And here you can see some results from a system that it's actually a small molecule on top of a metal surface. From that, you see that you can calculate the adsorption energy. Now, the absorption energy from that can be later or should be used in order to build a model, as we say in this bottom-up perspective, in the atomistic scale. In order to do this, we should solve a very complex, I would say, optimization problem, because we need to solve it over a many parameter space. As you see here, this is the coupling between the two scales. I don't need to give you a lot of details about this, but the main idea is that this is possible to be solved. And as you see here, you see the data with symbols are the data from the density functional theory, and with lines from the data from the atomistic simulations after solving this optimization problem. So with the new atomistic force field, and as you can see here, the agreement is excellent. So this means now that with this, via this bottom-up approach, the interaction with the density functional theory, it is possible to be described with this with some functionals in the atomistic scale. Then these functionals can be used in order now to perform simulations on much larger systems in the microscopic scale. And this is a typical example. So here we have now atoms in the microscopic, in the atomistic scale. Typically are hundreds of thousands or even millions of atoms nowadays. There are typical snapshots, videos out of that. What is the advantage now of these simulations? The big advantage over experimental techniques, I would say, is that we have the evolution of all atoms in the system. This means that we can really study and probe properties which are very difficult, if not impossible, to do it with experiments and even with extremely expensive and very complex experiments. And one example is that we can analyze properties for confined system as a function of distance from the surface. So here we have two different phases. We have here the polymers, and which are confined between solid surfaces. In this case, these are graphene. And then what we can do in the simulation is that we can analyze the properties as a function of distance from that. This is very nice, and typically we describe such simulations as, let's say, the perfect in quotas experiment, because we can get all this information. However, this is still not possible to calculate, to simulate and to study very large systems with atomistic simulations. That's why we need now to go, let's say, to a mesoscopic scale. And this, there are several ways to do this. In this systematic or bottom-up, as we say, approach, which is very quantitative, I would say, more rigorous, typically, we describe it. This is being achieved via projection operator formalism. We don't need to know anything about that. The idea is that we develop this force field, or the model, the mesoscopic model, using data again from the more detailed simulations. This is all the idea about that. And then typically, because, or in cases where we need the atomic detail, there are algorithms for reintroducing atomic detail when it is important. And here you see an example from where we have the description in all atoms, the black one, and then we have the description in red and blue, which are these coarse-grained, as we call them, superatoms or bits. So this is the coupling between the microscopic and the mesoscopic scale. And as I said before, typically we want also to have some connection with the atomic scale, and for that there are specific algorithms which are rather geometric. So here you see something like that. This is interesting because you see here the forward and the back mapping process. The forward is from the atomic scale, we go to the coarse grain, and this actually it's even a coarser description. So the same molecule is described via 3 different models. And then we have algorithms in order to reintroduce, again in a hierarchical way, to reintroduce details. So from the very coarse, we have here the moderate coarse grain model, and here we have the all atomistic one. And with this now methodology, this multi-scale methodology, it is possible to study really very large systems, long polymer chains. For example, in this case, we have polymer chains up to 100,000 molecular weight, and this is really relevant to the polymer processing. It's the first time that such simulations are possible to be achieved, and more recently we have also machine learning based approach for that. The advantage of the machine learning based is that it's more automated, I would say, in an automatic way. So here the idea is coming actually from the image analysis, is that we translate the coordinates and the configuration of atoms that we have in pixels, and with that then we can do the back mapping, as we call, or the introduction of the atomic detail on the coarse grain configurations in an automated way. Okay, and now why are we doing all this? Of course, as we said, our goal is to solve problems and to predict properties. And these are now in the next few slides just typical, a few, let's say, examples from our recent work. For example, here we have one polymer, is the polymethyl methacrylate, which again is confined between graphene. So this is a model of the polymer graphene nanocomposites, nanostructured materials. This is the chemical nature of the polymer, and here the question is what is the effect, or how the chemistry is coupled together with the interaction with the graphene. That was the main question, and the question is coming from experimental observations, where they see, for example, that the glass transition temperature, which is a very important property, macroscopic property of the material, because it's directly related with the mechanical properties of this materials. So it has been observed that the glass transition temperature changes from the bulk and changes differently for isotactic and syntheotactic. So the question is if this is true, and if it is true, what is the reason? And now the advantage of the simulations, as I said before, is that they can probe with the simulations, we can probe time scales and length scales that are not possible to probe experimentally. For example, here we see the density profile of the system. So it's the density of the chains as we go far away from the surface. 0 here is the position of the graphene seeds. And what we see here is the dense layer. This is actually, we expected a dense layer at the interface. It's because of the attraction between the polymer and the graphene. However, if you see the layer is slightly larger for the isotactic case. If you don't know anything about stereochemistry, it's not a problem. Consider that isotactic and syntheotactic, there are two different stereoisomers of PMMA, so they are exactly the same chemistry, but different structure of the monomer. However, you see here a small difference, and this difference actually results to a more dense layer, which, if we translate now this to the dynamical behavior, it results to different relaxation times as are typically quantified. If you see the isotactic here is larger all the time. And now if we translate this to macroscopic properties, and as I said before, the glass transition temperature is a very good example, then you can see here that the difference with the bulk, it's different, it's much different for the isotactic than for the syntheotactic and the atactic. And actually not only that, but if we probe only, as we call here, the first layer, so only the region at the interface, then the difference is even larger. Yeah? Whereas for the entire film, the difference it's about 10 degrees here, and for the syntheotactic is only 4. So you see here directly a coupling, and the better packing at the interface leads actually to stronger influence on the dynamics and also to the increase of glass transition temperature. So this is a typical example of how a microstructure or atomic structure is being directly, let's say, determines the macroscopic properties of the materials. Another now family of systems are polymer nanocomposites, and again here you see a video from the simulation. So here we have the polymer and the nanoparticles inside them, and again we can analyze the systems. We can analyze them not only now as a function of distance, let's say, from the interfaces, but also for the different conformations along the chains. And we see here that the behavior of the chains is different, whether we have adsorbed chains, which typically are called trains, whether we have segments that are connect trains, or when we have either segments that bridge two different nanoparticles. So all of them have different behavior, and this is important because the simulations can give you direct way to study these differences and to predict. For example, here again you see the ratio of relaxation times for these systems over bulk relaxation times for different conformations now. So again, this is a property that cannot be, I would say it's impossible to get it from experimental techniques. And not only that, but again, we can calculate properties, or we can compute properties that are more related with the macroscopic level as the diffusion coefficient. The diffusion coefficient is probably the most important property that is related with the mobility of these materials. And then, as you see here, we plot the diffusion coefficient as a function of the number of monomers or the molecular weight of the chains. And the important thing here is that, if you see here, this is the bulk system, and this is the nanocomposite. So all the time, the nanocomposite is above the bulk for the same molecular weight, which means that the nanocomposite systems exhibit a slower dynamics than the bulk ones. And these are now the theoretical models. It's not so, they're not really so important for someone who is not in the field. And not only that, but we can also calculate properties which are even directly related with the processing. So when we discuss the processing of this material, the shear relaxation modules is an extremely important quantity directly related with the mechanical properties. And here you see now that this is predicted directly from first principles. Again, this is for such molecular weights, it's the first time that it is possible to calculate. And here, actually, we see a very nice comparison with experimental data. G prime and G double prime are simply the real and the imaginary parts of this quantity. And then you see also some comparison with the symbols here with our experimental data, and the agreement is excellent without actually any fitting. So we have direct comparison. Now, besides this, which belong to what I've said as polymer nanostructure materials, different type of materials are star polymers, for example. These are used for a very broad range of applications nowadays. And then star polymers have this specific architecture. So if you see this architecture, this cartoon now, you would assume that these are like spheres, but this is not the case. So if you see here, they might have different shape, and actually the shape depends on the number of arms that we have here. As you see, from linear polymers, these are more like to linear, which are an ellipsoidal. Then we go to a more colloidal nanoparticles, which are more spherical and exhibit a different behavior. So this is extremely important because the difference in the shape here, again, it affects the properties. And not only that, but if we have now within the same particle different components, so this means simply different here arms with different chemistry, then you might see such much different or much complicated phase diagram, I would say, in quotas of different shapes, which depends on the actual chemistry of these two components, which don't like each other, and the interaction with the environment. Here is in 3 different environments: vacuum, polybutadiene, and the selective one. All of them, we would say, from the point of view of physics, that are minimum free energy, but they are also important from the point of view of engineering because they change the properties of the materials. And other applications are related with the graphene-based materials, as I've said in the introduction, related with, for example, graphene-based nanocomposites, extremely important. And the main here challenge is to describe the anisotropic behavior, because graphene is an almost 2D material. So this anisotropic behavior determines the properties of these materials. And not only that, but this affects also important phenomena such as crystallization and melting. Here you see the polymer chain, how it's a crystalline polymer chain, and you see the crystallization process, the formation of a perfect crystal on the surface. Again, this all studied by atomistic simulations, and actually this is a reversible process. So you see here, when we increase the temperature from the crystal structure, we go to an amorphous light, and then by decreasing temperature, we have, of course, the reversible process. And a last example, it's related with the biomolecular systems, which again, it's a main activity, and it will be a main activity in our project, especially nowadays with this Green Deal that we hear every day, with the cyclic economy. The development of biodegradable and low cost, I would say, eco-friendly, as we call typically, synthesis, it's a main challenge. And a family of systems that are candidates for that are biomolecular systems that are being self-assembled. So there is not really a real synthesis here, but the materials are being self-assembled into structures, and from that we can have macroscopic structures via self-assembly procedures, which are much more, as we say before, eco-friendly. And then you see here, this was a very nice, actually, collaboration with experimental groups, where we see the microstructure from the simulations and the macro from complementary experimental techniques. Now, this was just, a very, I would say, very fast presentation of a few examples from research. Now, the last part, and the next, I would say, 5 or 10 minutes, I would like to just emphasize a little bit the rest of the objectives of the SimEA. And these are related primarily with innovation actions. The main thing is this is something that actually would be coordinated together with not only the Castor C, but another European project that has been started a few months ago, the ERA-HPC. And actually, Castor C is a national competence center, and ERA-HPC now is directly related as part of the ERA-HPC joint undertaking. And the goals, it will be to provide a service portfolio for national needs to industry, academia, and public. And actually, these are also main goal of the SimEA. So there are these coordinated, I would say, actions between the SimEA and the EURO-HPC. And the idea of that is to together, I would say, these projects and to advance and to emphasize the national competence center nature of Castor C, and to advance the competitiveness in computational research, to improve the effectiveness, as it's written here, from public services, and primarily to, I would say, to engage industry, which is the main action. And now all this will be performed under the, or at least with the help of the Management Innovation Office. This is a new office that has been established a few weeks ago at Castor C and the Cyprus Institute. It's currently consists of Christos Christodoulou and Kathy Christoforou, which are, as we said before, Innovation Scout and Scientific Coordinator of SimEA, and Andreas Gavrilidis, which is Scientific Coordinator of Stimulate and other European projects at Castor C. And now the main scope of this office is to forge links between academia, industry, and government. This is a primary importance for us. And as I've said, we would like to create new collaborations and to emphasize the role of the hub under SimEA. And in general, we are not limited in the field. So in general, in the fields of high-performance computing, AI, as we call it quite often nowadays, since it involves all algorithms and tools, and also the data science. And because of that, there will be also some activities. I hope that you will be all informed about them within the next weeks or months. There will be industry weeks. The first one, it will be most probably the first week of March 2021. There will be several training program events. There is the possibility for collaborative projects. And of course, the seminar series. This is the first one, but we would like to have at least 1 or 2 times per month, so every 2 weeks. That is our plan. And just as a general, I would say, remark, one of the first things that the MIO office has done is a first market analysis. Market analysis together with the Cyprus Statistical Service. And here is, you see something that for me at least was very interesting. I didn't know, I was not aware about that before. So here you see some statistics during the last 2 years in Cyprus. So you see here the companies that are involved in analyzing big data. And from we don't have data for 2019 and 2020. But you see that within 2 years, we have almost double the number of companies which are very interested in analyzing big data. So it was from 85 to 169 within 2 years. At the same time, you see here that the companies that utilize computing power in cloud services, which again, it's within 4 years, it's more than 4 times up. So there is really huge, it seems that despite the fact that, of course, Cyprus is a small country, but there is a huge need here for big data, for simulations, for computations. And last, just to close here, that these are coupled directly with the infrastructure. So this is, as we say, typically a conditio sine qua non. So it's indispensable and essential condition. Without this infrastructure, nothing can be done in this area. And this is the infrastructure at the Institute. We're very happy with that. It's one of the biggest in southeastern Mediterranean. However, we anticipate to be further extended within the next few years. And this is extremely important. So I'm just here just to remind you, nowadays this exponential growth, unfortunately due to the COVID, is very popular. But just to remind you here, Moore's law, I mean, I'm sure that all of you have heard about that. And this was it was an empirical, actually, law proposed by Moore, that the number, and it's based on the fact that the number of transistors in this IC, in integrated circuits, doubles approximately every 2 years. And it's remarkable because this has been started during the 70s or 80s, and up to now, it's still valid. So of course, this cannot be valid forever, but it's still valid. And because of this now exponential growth, this means also that the problems that are nowadays that we can deal with are really much, much more advanced and complex what we could 10 or 20 years ago. So I will probably, this is the last slide. Here is just from the historical context. So this is a main property. Again, it's a shear relaxation modulus. So this has been calculated from atomistic simulations in almost 15, 17 years ago. At that time, it was the first time that we were capable from atomistic simulations to predict rheology. However, the systems here are, as you see, very small. So we consider systems at that time of only 1,000 up to 10,000 atoms, a very short polymer chains, only 3,000 molecular weight, and simulation times of the order of 10 or up to 100 nanoseconds. What we can do nowadays with, we can simulate systems with at least 2 or 3 orders of magnitude larger, millions of atoms. At least, again, I would say 2 orders of magnitude longer chains, 100,000 molecular weight, and 3 orders of magnitude more time. And this is really before the exascale. So all these are part of the still, let's say, petascale regime. So we anticipate that in the exascale, the advances will be really even larger. So, and that's my personal, I would say, message, especially to the young people. I think it's really a fantastic time to be involved in this field. So I will close. I should acknowledge several people. The research examples that I show you are from since we have just started now here. So these are from my team in the University of Crete and the Forth. So all these people here, collaborators all around the world here, are just the people who were involved in the project that I present you. Funding from European Union, Greece, private sector, etc. Finally, of course, I would like to acknowledge, and as I've said, I feel really honored and lucky because we have an excellent team here and we are very enthusiastic. And last, I would like to thank all the people of Castor Sim in the name of Director Konstantinos Alexandrou, Dina, and primarily many thanks to 2 people, to Andreas Gabrielidis and Nikos Bakas, who helped us really a lot with the coordination of the project till the formation of the research team. So thank you all for your attention. I will be happy to answer any question.
Thank you, Professor Harmandaris, for this very interesting and the introspect of the presentation. If you have any questions, please feel free to submit them now in the chat or the YouTube live channel. I mean, as far as I can see, we have no questions at this moment. Well, in any case, I mean, I will just say that feel free to visit the webpage of the project so you can see in depth what we have, what the current achievements are, and the project itself. And
if I may, last word, Andreas.
Yes, of course.
I would like, just as you said, because I don't know even if people can now take even if they can ask directly, let's say, but I would encourage everyone. Okay, it was a lot of info, of course, in this presentation, but I would encourage everyone really to not hesitate. Please ask us, contact us. We will contact you, many of you, and the idea is really to build something that is going beyond the life of the present, let's say, project here.
Exactly. Okay, thank you very, very much again. And to everyone watching, have a great afternoon. And we are at your disposal as Castor C and as the team of the SimEA for any questions or remarks you may have and for any communication you may need. Thank you very much.
Thank you very much.
Coarse-grained simulations for systems under flow from Pavlo Stefani.
This is very, very interesting question. So actually, it's a field that we have worked in the past, and it's again one of the directions we would like to do. This is something that it is doable because in principle you can, so if we go, let's say, back here, just as an example of this work here, the thing that we should, let's say that we have the atomistic model, and then for that we apply the flow field, let's see here this example, for example, for this. I found it. So we have this system now. This system is under equilibrium. So what you see in this movie are actually more or less the Brownian fluctuations, thermal fluctuations of the system. So if we apply the flow field, and there are ways via non-equilibrium molecular dynamics simulations, non-equilibrium that I present here, then we have the flow field. Now in the coarse grain level, we need two things. We need first, again, to apply the flow field via the equations of motion, and second, to have the proper force field. So the force field is being developed, again, via this parameterization technique that we present here. Now, this technique is valid, let's say, close to equilibrium. If we are far beyond equilibrium, it's a very challenging field. Why? The reason is that this approach here is based on statistical mechanics. And if we are far beyond equilibrium, then the basic concept of statistical mechanics become questionable. So this is, let's say, from the methodological point of view, this is a very important aspect. I hope I have answered the question, but I'm sure that we will have the opportunity to discuss this in the future with Pavlos.
The questions-wise, that's all we have. So thank you again, and thank you everyone for being present. And yes, have a nice afternoon.
Thank you.